Okay, ready? So welcome back. It's my pleasure to introduce Gabriele Benedetti from Amsterdam. Is that right? Yeah.
Yeah, that's
and he's going to talk about rigidity and flexibility of periodic Hamiltonian flows. Thank you, Gabriele.
Yeah. Thank you for the introduction. Thank you for the invitation to Lucas, Umberto, and Vinicius. I'm really enjoying this week, seeing how different talks from people from different areas touch upon each other so nicely. So it's really amazing. And today I want to talk about some joint work with Lucas Selle from Bochum and Massimiliano Berti from SISA Trieste about rigidity and flexibility of periodic Hamiltonian flows. So we have seen already how having a Zoll metric, so a metric whose geodesic flow is periodic, is related to systolic inequalities, because they are kind of the local maximizer for such systolic inequality. But actually, the rephrasing of the systolic inequality for rep flows does not just confine ourselves to the world of geodesic flows. So we can also think, we take our favorite Hamiltonian system and we look inside the class where the system lives for examples of such periodic things. And so today, the spirit of the talk is to go a bit in this direction, and the class I will be interested in mostly will be the class of magnetic flows. Okay, so let me first set the stage, and if you have any questions at any time, please feel free to stop me. Okay, so the general goal, you have a symplectic manifold, and then you consider a class of Hamiltonian systems, H lambda, where this lambda lives in some parameter space. You can think this is a space, for instance, of Riemannian metrics, or we will see also today other examples. Consider a class of Hamiltonians. And then what we want to do, we want to look for examples of H lambda such that the Hamiltonian flow at energy H is Zoll. Okay, so this means basically that the flow on the hypersurface is a free exponential. And this time, I need to add a little caveat up to global smooth time reparametrization. Global smooth time reparametrization. Okay, so here, I mean, a bit of a difference with the geodesic case that we also need to kind of be sure to specify which energy we are talking about, because usually the systems will have different dynamics for different energies, and also sometimes the orbits will not have the same period. We will see that they will have the same action, but also the period might be different. So you also want to allow, if you want to have something which is really close up in the same amount of time, to allow for a smooth time reparametrization. But the picture, the geometric picture is the same as the one of kind of Zoll geodesic flows. All right, so what is the idea? We want to kind of try to explore and find examples. So that is, we start with some trivial ones, and then we deform them using this implicit function theorem. It was also mentioned in the talk by Andrea before. So the idea is that we start with some parameter lambda 0, such that this H lambda 0 is kind of a trivial Zoll example. So for instance, think about the round metric on S2. And then what we want to find some function SH, which depends on this energy, on the space of parameter inside some target space, such that SH of lambda is equal to 0 if and only if H lambda is Zoll at energy H. And then we want to apply implicit function theorem to this. So then use implicit function theorem to find lambda close to lambda 0 with H of lambda Zoll at energy H. But so this kind of the idea. Then usually this is like an infinite dimensional space. So there will be some analytic issues when we kind of study such problem. The main analytic issue is that this functional SH is not C1. So that is an issue. Oh yeah, I've written it in an export. So the main analytic issue is that this function here is, in general, is not C1. So you have some problems when you want to apply the implicit function theorem. SH is not C1, and therefore, like kind of solution to address this is a mix of two things. So the first thing, you will use the Nash-Moser version of the implicit function theorem. But then still, you have the issue that if you want to apply implicit function, you want that the differential of the functional is surjective in a neighborhood. And for this, you need really to look in the eye this functional and study it with the theory of Fourier integral operators plus theory Fourier integral operators. And these already appeared in the conference. Also yesterday when was Luciano's talk, he considered this radon transform, and to study it also, and we see also that this appears, you need some nice and careful analysis. So today I'm going to give a bit of the sketch for the case of magnetic flows, and I will say something about this, this analytical part. All right. So this is the idea, and then also what will be the outcome of this, if we can maybe summarize it, is that we will have flexibility. So we will be able to run this machinery to find non-trivial examples for a single value of H. But you will have instead some rigidity phenomena for requiring, let's say, Zoll for many H. Also, this, I mean, you can think that for each H I might find some deformations. And if I can start thinking, OK, what if I want something which is kind of Zoll for many values of the energy, then actually you will find instead there some rigidity phenomena. So this rigidity goes back a long time. There is an old result in celestial mechanics, but in general in classical physics by Bertrand in 1873 that tells you that if you have a central force such that all closed orbits are periodic, and the orbit is somewhere attractive, then it's either the Kepler potential or the elastic potential. So this is kind of an example of a result where if you require a lot of periodicity for many values of the energy, then you get rigidity. And today we also see this phenomenon for the case of magnetic flows. All right, any question before I move to the definition of magnetic? All right, so let me briefly introduce the setting, since this will also be used by Valerio, I think, in the next talk. Okay, so what are for us magnetic geodesics? So we have here Q closed manifold. Then you have G Riemannian metric on Q. And then you have sigma closed to form on Q. This is called the magnetic field. Okay, and then to these two objects, I can associate the Lorentz force. Which is an endomorphism of the tangent bundle, which is basically the endomorphism representing sigma with respect to the bilinear form G. So then you define it this way. Sigma uv is actually the metric of y times u, comma v, and for all q, and for all tangent vectors. All right, so once you have the force, now you just define solutions to the Newton equation corresponding to this force. And you have your magnetic geodesics. All right, so then a curve Q from R into capital Q is a magnetic geodesic if the acceleration of Q is equal to the Lorentz force applied to Q dot. Now, so this you can think this is a generalization of the geodesic case. So for sigma equal to 0, we get classical geodesics. But in general, these two terms scale differently with respect to the speed. So you will see that for high energies, this is the dominant term. So you have just a small perturbation of the classical geodesic equation. But for small energies, then this is kind of the dominant term, at least when this guy here is non-zero. And so you see like more curved phenomena. And indeed, they are kind of, in the two-dimensional case, related to curves with prescribed geodesic curvature. And this brings us to the talk of Jean of yesterday. And this is actually the case we will be mostly interested in. So the case of surfaces. So if you take SQ an orientable surface, so S2, T2, and so on, then in this case, you write your sigma as some function times the area form. And then you know that Q is magnetic geodesic. if and only if the geodesic curvature of Q is equal to f of Q divided by the speed, by r. And I can say here Q magnetic geodesic of energy h, which is 1/2 r squared, and this is the r. No? So this r is the speed. All right. And this is the geodesic curvature. Right? So this like the case of like hypersurfaces in 2 dimensions such that the mean curvature is prescribed. And in general, they are anyway Hamiltonian systems, where basically the Hamiltonian is just the kinetic energy, and you just twist the symplectic form using the sigma. So let me write it down. So in general, a Q lifts to Hamiltonian trajectory of in, let's say, in the cotangent bundle of the kinetic Hamiltonian with the symplectic form, which is the standard symplectic form, minus p star sigma, where p is like just the projection. Okay, so you twist basically the symplectic form by this magnetic term, and you can think that okay, for different magnetic terms you have different actually symplectic manifold. But we will see today that if you kind of fix the cohomology class of this person, then basically the difference is just an exact form that you can use to do a symplectomorphism that goes into instead a Hamiltonian. No? So maybe I can just write it down. So if sigma tilde, let's say, is sigma plus the differential of some other things, eta, then you have that the h as above and omega as above. This here is equivalent to h tilde, where I put 1/2 I think p plus eta squared, and here is p star sigma tilde. So you can always change, and then basically the symplectic manifold will stay the same, and then just changing the Hamiltonian by this.
That in general means here always or usually?
Sorry?
Yeah, no,
Always. Here means in general with respect to this orientable, the surface case. So in every dimension, this in general means in every dimension.
Oh.
Okay, yeah. Yeah, other questions?
And can we think of
Yeah.
those geodesics as geodesics in some connection? So we deform the connection, just limit the connection by adding this Lorentz force operator, and those geodesics are just like this.
Yeah, I think so. If you can think of them as so, since they live on the unit sphere bundle, you can think of a nonlinear connection on this unit sphere bundle. But so this y there brings some nonlinearity. I mean, in the connection, or you need to enlarge, or also what you can do, you need to enlarge to lift maybe 1 dimension higher, and then you can see this as trajectories embedded in a standard linear connection. Yeah, no, that's good. Other things? Okay. So this was why these things are Hamiltonian. And then we will be mostly focusing on this surface case. And here you have kind of trivial Zoll examples. Where basically now we are restricting just to the case where sigma is not identically 0, because otherwise we have the geodesic case. And then you just take Q orientable surface, and then you take as G of constant curvature, and F constant function. Okay, and then what is the energy? The energy must be sometimes restricted, belongs to some interval 0, H0, where this is related to the Magnier critical value of the system. Also, if you think what happens in the hyperbolic case, these are curves with constant geodesic curvature. And then you know that, for instance, you have the orocycle flow, where this geodesic curvature is equal to 1, for which the orbits are not actually closed. But if you go sufficiently low in energy, then all orbits actually will be closed. Okay, so our idea now is like to deform these examples, and we'll be mainly interested in the case of the torus. So I'm going to use the write-down notation. So today, yeah.
What is the parameter H again?
H is the energy of the system, the kinetic energy of the system. So here you can think you are just scaling the geodesic curvature. But in general, it's like the energy of the Hamiltonian system.
So when you say it's Zoll family, so you have what? Families of constant curvature curves?
Mm-hmm. Yeah.
And what is H naught?
Sorry?
You put H from 0 to H naught.
The Magnier critical value.
What is that value?
The Magnier critical value, I think.
No,
H not the Magnier critical value.
yes, sorry. H naught is the Magnier critical value. So on surfaces, maybe I can say so. If Q is equal to S2 or T2, then actually this H naught is equal to infinity. Yeah. And then it's 1, yeah. And then Q hyperbolic, then this H naught basically is related also to this orocycle flow. No? So in this case, when you have hyperbolic, then you know that if you have geodesic, you arrive here orthogonally, and then if you start increasing the geodesic curvature, then this angle starts decreasing, and at a certain point you have the orocycle flow, this H0 equal to 1, and then after that you have an honest Zoll example. So for instance, let me say here that today we focus on T2. This is where the analysis is better. In this case, you have basically Zoll, trivial example. Orbits are just Euclidean circles. And circles, CR psi, radius R, and center psi. So it's like, in this case, like a T2, it's a T2 family of orbits. All right. So this is the setting, and I want first to present like the rigidity result that we have in this case, and then we move to the main result, which is the flexibility. Are there any other questions? So rigidity theorem. This is due to Selle, myself. It says the following. So if Q is a two torus, or actually any orientable surface is also fine, and sigma is not identically 0, so we are not in the geodesic case. And you know that there exists a sequence Hn converging to 0, and there exists Hn converges to 0 such that magnetic flow is Zoll at energy Hn for all n, thus this implies a trivial Zoll example. Also here the idea is that if you have this Zoll property for many values of the energies, and in this case it's enough to have a sequence going to 0, then you just have these trivial things over there. And you can start thinking, I don't know, maybe what happens if you have just two values of the energy for which it's Zoll. Finally, many of you can find also other sequences having such a rigidity. These are all very interesting questions. And for instance, there is Christian Lange and Lucas Selle who worked also on other cases of this theorem. For instance, looking at what happens when this Hn converges instead to 0 to this H0. All right, so this is the rigidity. And now we want to do the flexibility result. So this, yeah?
So you say you focus on T2, but the theorem will be at the surface?
Yes, this is, yes, so for the flexibility we focus on T2, but yeah, this works on every surface. But also on T2 is non-trivial theorem, yeah.
And by Zoll family, in that case, so if it's on the T2, it's a T2 family?
Yes, it will be a T2 family. Actually, there's not.
Surface is what? Is a Q family?
Yes, it's always a Q family. Actually, there are also some topological restrictions. For instance, on the two torus, you know that the rotation vector must always be equal to plus or minus 1, so you cannot have stuff like this that arise and give you Zoll stuff. All right, so now flexibility theorem. This now will be really on Q equal to T2. So we think of this with coordinates, let's say x, y. And then we fix the energy, h, which is 1/2 r squared. And then we want to also parameterize our magnetic systems. So for us, we will take as G parameterized by A. So this is 1 plus A squared G0, where A now is a smooth function with 0 average. This is just to make things a bit nicer in the computation. So this is a 0 average. Right here. 0 average. And then for the magnetic term, we also can parameterize it by a function, because basically what we will do, we will just fix the cohomology class of the magnetic term. So then basically all you need to specify is an exact one form, and this you do just up to, sorry, you would just need to specify a closed one an exact two form up to closed one forms, and this is like just given by functions basically. So let me write the formula that also we use. Okay, and for sigma, we parameterize it by B. And this is basically you start with the area, and then you perturb it. And to make things nice, we perturb by R. And here comes the square root of minus the Laplacian, and then times applied to B, and then times the area. Okay, so this is just the Laplacian of the standard G0. This is just to have a nice deformation of this by an exact one form that kills all the kind of possible gauge that you have. Okay, and this B is also a function with zero average. All right. So now we're basically parameterizing our systems by this pair, which are two zero average functions. This is our space of parameters, if you remember the very first thing. And then when AB is equal to 0, 0, then you have this trivial Zoll. Trivial Zoll. So we are just doing implicit function starting from this. And now we can state the theorem, which is basically, you will see formally the same statement that was also presented by André before, this Guillemin result. And is a theorem that in this generality is still work in progress, but we proved it already in the case of integrable systems. So this is in general in progress, but is for when A just depends on AX, on X, and B just depends on B. This appeared already a couple of years ago. Okay, so what you do, you take any kind of alpha beta in this space of parameters, and then you have that there exists there exists a path, tau, A tau, B tau, in the direction of alpha beta. So this is like tau alpha beta. Let me write like this. Tau alpha, tau beta, plus higher order. Deformation of Zoll. By Zoll at energy 1/2 R squared. And this if and only if alpha beta belongs to the kernel of some radon-like transform. And this I call it R0, I think. Yeah. Okay, so there is now I'm going to explain what this is. It has a nice formula. And this is a sort of magnetic generalization of the standard radon transform. Okay. So where? This is an operator, linear operator. It goes from zero average to functions with zero average and gives back one function with zero average. And how is this function here defined? Let's say, let me call this gamma. What is gamma? So now gamma takes value psi. So this is, I write it also in this way. This is defined as you integrate alpha along circle times the line element, and then you subtract an operator times beta, where this operator here, D is just Hodge star, and then you have, what do you have here? d, and then you have minus 1 over 2. Okay, so you can think this is basically similar to what appeared yesterday in Jean talk, so where he had the length, and then here is the area, basically. And we choose here to do this parametrization using the Laplacian here in such a way that now this operator here is of order 0. So this is operator of order 0, such that these two pieces have the same order. And we will see for the proof it's important to have a nice interaction between these two pieces.
You are integrating over what?
This is the circle of radius r. So you take your point psi on the torus, and then this is the circle of radius r. So it's like that's all trajectories in this case. All right. So this is the statement of the theorem. Like maybe remark. So in the given case on the two sphere, instead of this alpha beta, you had odd functions. But also odd functions can be interpreted as the kernel of some radon transform, namely you integrate along great circles on the sphere. And here is kind of a similar thing. You don't have a nice description as a function being odd, so you just have the fact that this pair is in the kernel of this operator. But still you can say many things about this operator. Maybe I can write here as a remark. Is that this kernel is infinite dimensional. And you can also write down this operator in Fourier modes in a nice way, which really shows that there is a nice interaction between the two terms. So let me do that. So, right. Maybe I can even do it here. So if I do R, 0, 0 of alpha, beta, psi, so now we have a Fourier expansion. K is in Z2, different from 0. And the Fourier multipliers are given by the Bessel function. So here you have J1. Let me get the formula right. You have J1 prime R K times alpha hat K. And then you have minus I J1 R beta hat K. So these are the Fourier coefficients, and then, okay, you multiply by the Fourier basis. All right. So from this formula in particular, you see that this operator is a surjective operator. So it's surjective. Why? Because the thing that you need to see here is that basically these two terms, they cannot vanish at the same time. No? So if you have this term and this term here, they are never 0 simultaneously, because this J1 satisfies some linear second order ODE, because J1, this is the first Bessel function, satisfies second order linear OD. So this, actually, if taken separately, these two terms are, in some sense, behave very wildly with respect to R. because basically you see here you have r times norm of k, and since k runs over all integer points, then this thing, if I change r, I could maybe create zeros or not. Same here, but if you put them together, they are very happy and they can compensate each other in such a way that the total operator is surjective. So singularly, these operators were studied a lot in the literature, for instance, in the setting of Pompeius problem, or also in the case of the two-sphere, these were studied, and these phenomena were observed. But here we see that if we consider them together in the realm of magnetic things, they are kind of best friends. All right, so this is the statement. Any questions about the statement of the theorem? So now I want to give, in the remaining time, a bit of an idea of the proof. And I mean, this proof kind of mimic a bit the idea of Guillemin for the case of S2. But I must say we also kind of followed even more kind of closely the approach of Ambrosio, Neves, and Marquez, because this is like a variational approach, as Andrea was saying before, and also for us it came a lot more natural than Guillemin's approach. And also this has some connection to a theorem of Botkol about normal forms, was mentioned by Alberto, so it kind of fits nicely in the picture. All right, so I want to give then a sketch of the proof. Okay, so proof strategy. Okay, so what we do, we want to characterize variationally. So we take L, this is the set of contractible loops. Q on T2. So every contractible loop comes also with a capping disk. This is a capping disk. And then you consider the action. So SRAB. This is basically the same thing that appeared yesterday in Shintok. So this is just the length. So I do integrate over Q ds G, and then I subtract 1 over R. This was C in his talk, Q hat sigma. Sigma B, and this is GA. Yeah. Okay, so this is the action, and then you know that Q is a critical point for this, if and only if Q is a magnetic geodesic with energy 1/2 R squared. So basically, so the Zoll case will be when I can find a T2 family such that this function here is kind of constant on this T2 family, and this T2 family actually will be kind of a particular type. So first I want to define what this particular type is, and then basically our condition will be just to assume that this function here is constant on this family. So we have a nice family of critical points for the functional. No, and the starting point will be the case AB equals 0, 0. So we have that we have a T2. Let me call it T2, 0, 0. Inside the critical points of this SR 0, 0. And this is this family of Euclidean circles. And now I want a lemma that singles out for me a nearby T2 family, which is a candidate for my Zoll family. And for doing this, we are just going to use that actually this manifold here is a Morse-Bott manifold for the functional. Okay, so we are going to use basically the following lemma to find these things. So if you have some AB close to 0, 0, then I can find this family T2AB contained in the loop space. And these I just denoted in this way, CR psi AB. With the following property, such that if I now take the restriction SR to this family, so this is so what I'm doing, I take AB and I associate to this the action on the family. Is it all the parentheses? Yes. No? So this is now a function that depends on xi. No? This is xi. Then you have the condition that AB is Zoll if and only if SR is actually constant. And in this case, the family is your Zoll family of Zoll trajectories. In this case, this T2AB is family of magnetic geodesic. All right, so here really the idea is to use the fact that this is a Morse-bot thing. So basically you start with the unperturbed thing is a Morse-bot component. For SR00. So this means that if I split now the tangent space, so the loop space as the tangent space along the torus and the kind of complement, then this SR00 is Morse on the complement. And so now, if it is Morse on the complement, basically, if I perturb, I will see in each fiber critical points for the restriction to this vertical component. No? So now is the following picture. I have here my T2, 0, 0. And then here I have this kind of orthogonal complement. And then if I look now at the restriction of the perturbed functional on this thing, I will find here a critical point. No? So this is like a critical point of SRAB restricted to W. No? And this will form now my nice perturbed thing. And since now I'm just saying here that this, in this vertical direction is a critical point, the only thing that I need to have a global critical point, so magnetic geodesic, is to have that also in the horizontal direction I am critical. But since now this is like a nice manifold, this is basically just saying that I'm critical along this submanifold, which is the same thing as saying that my function is actually constant along the submanifold. So that you have the kind of the equivalence between being constant and being like a critical point. So this is like a bit of sketch of the proof. All right. Any questions about this? Okay, so I don't think I will have time to do the whole thing. Maybe I can just say how this now radon transform pops up. So I want to do the differential of this thing. No? So I want to say, to apply to apply implicit function theorem, then I need the differential of this thing with respect to AB. And now this thing has two pieces. So if I differentiate, I have a piece here and a piece there. And then for one of the two, you will see I will get the Radon transform. So then this ds RAB. If I differentiate in this direction, I have basically two pieces. And the first piece will be the Radon transform, but now at a nearby point. Yeah. And if I differentiate the second thing, I will get just the differential of this in the direction of these perturbed circles. Okay, so now this RR is just the same definition I had before, but I'm now integrating not over the standard circles, but over this family of circles. So now this is just alpha beta. You integrate along this family, alpha ds G0 minus d beta. All right. And basically, this term here is the term that you want to control. The other term is actually, you can think of, is of a lower order, because if you are a Zoll thing, then you know that here this will be 0, no? Because this will be a critical point. No? So if AB Zoll, this implies that this differential is actually equal to the Radon transform. No? So then basically this is the thing that you want to understand. And for AB equal to 0, we've seen that this is surjective, but in general, this is like a more delicate problem to show that this is surjective also for AB close to 0. This is also a problem that actually Guillemin had in his proof. And so here the idea is to kind of look at this normal operator, but I'll just maybe say a few buzzwords and then we stop. So now the issue is that if I do the map from AB into RR AB, this is not continuous. You can understand a bit why, because, for instance, if I take this term here is something like something of the type, you integrate over some parameter, let's say 0 to pi, you have alpha of this CR psi AB, and then you multiply by the norm of this tangent vector, say dt. And now this is like a composition operator. And these are things which are not nice. So indeed, if I want to estimate for this in terms of what I know, for instance, in the 0, case, then the way to do this would be to apply, I don't know, other fundamental theorem of calculus. So this is like integral between 0 and 1. And you need to differentiate alpha and multiply by the derivative of this thing in the direction of SA, SB. So you see here now, this thing loses one derivative. So even though maybe you can control this term, this difference, you cannot just control it in this way. So you need now to fix is to look at instead AB going to the RRAB RRAB star. This will be instead continuous. Okay, and again here, what saves us is the interaction interaction of alpha and beta terms saves us in some sense. Now, this is not kind of something that you always have. You need to understand a bit this operator. And again, this nice interaction that was clear in the case 0, 0, also here will give us that this operator here is continuous, and so then you can invert in a neighborhood. OK, I think I'll stop here. Thank you.